All right, I'll lead off here. Just want to thank everyone for taking some time this evening to listen through our presentation. We're here to present the water distribution system hydraulic model that Arcadis worked with the town on. And my name is Michael Quinn. I'm the project manager. I've been working with a team. Ben's been leading our technical side. He's going to actually walk us through the bulk of the presentation this evening. Ben's been involved since the very beginning of the project, which I believe was back in 2020. We also had a lot of help from the town, specifically from Bart and Chris in the water department. Um, the model is only as good as the inputs. So we really worked a lot of back and forth trying to get all the right sizing of pipes and connections into the model so it could pretty closely replicate existing conditions. And, Ben will walk us through some of the specifics there. Um, but if I could just back it up a little bit, I guess the generator of this project was ISO, the Insurance Service Institute, doing a evaluation of the fire system and requesting some fire flows to do an updated rating for the town. And I think you can go to the next slide, Ben. So we worked with the town to essentially create a model of the water system in the computer. We did some field testing of something like 20 different fire hydrants to try to calibrate the model to pretty closely replicate what the conditions are in the field. And besides just the pipe sizing, and Ben could walk us through some of the inputs, but we also needed to characterize the condition of the pipe. And so we basically constructed a piping network in a computer software program. We used the field data, which we worked with the town on to calibrate the data outputs that we were getting. And then we used the model to try to see where some of the issues are in the system. The main goal, of course, being to get the available fire flows from each of the hydrants. There's something like 1,300 fire hydrants in the town. So using this model, you could go through each hydrant, and that was one of our deliverables to the town, the available fire flows for a fire situation. And we went a little bit further with this model to look at maybe some future improvements, looking at some relining projects and some upgrades. I know there's an RFP out right now to do a replacement of a 6-inch diameter pipe. So the model could be really good when you utilize it in that way. So you can understand if you want to replace it with a 12-inch or a 14-inch or 16-inch. So if the model is accurate, you can use the type of data that you can get there to right size your system. And I think we have talked to Bart and the town, continuing to keep the model updated as improvements get done over time. And I think this could also be a great tool for some of the capital planning that you guys do on a regular basis. So that's kind of the objective here in the summary of what we did. Ben's going to walk us through some of the specifics of how the model was created and how we got to calibrate and utilize it.
Yeah, so we'll back up first and give some background and context on hydraulic modeling in general. This is specifically distribution system hydraulic models, so they're hydraulic representations of the full system. And what that means is that there's a simulation, they're computer models, but there's a simulation in the background that is actually calculating all of the hydraulic conditions, the pressures, the flows throughout the system. Before we can actually simulate those conditions, we actually need to build these models. And these models include three different categories of information. First is the infrastructure, so the actual pipes that are in the ground, all pumps, all storage tanks, and the treatment plant that is actually feeding the system. So that's the first main component. The second main component are operational information. So how are those, say, pumps actually operated in the system to fill and drain the different tanks, for example, or how is the treatment plant operated to provide water to the system? And that's all plugged into the model as well. And then the last component is the demands. So that is the water use information at each, for example, customer location. That includes both location, where the water is being used, the volume, how much is being used at a given location, whether that's a house or a wholesale customer or an industrial user, for example. And then how that demand or water use changes throughout the day. When do the peaks occur, so that we can all represent all of those different conditions in the model. These models are all in specialty software. So the Towns model is in the Bentley platform, which is one of the main software platforms that handles both building the model and also simulating and using it for analysis. So the actual hydraulic components are actually, and all the formulas and understanding where the pressures and flows are, is handled by the hydraulic engine, which is the EPANET engine. It's actually a kind of the industry standard for these types of models and simulations. It's been around for at least since the 1990s, kind of has history before that. So it's kind of been in place, it's improved throughout the years and gotten faster over the years, but that handles all the simulation components. And then the Bentley platform is kind of built on top of that to provide the user interface, usability, kind of being able to extract out those results and maintain the model. These hydraulic models typically require a lot of data sources, and we'll go over some of what that entailed for the town in a couple of slides. But it usually is multiple data sources, things like GIS and facility drawings and customer water use information. And then once all those data sources are compiled, then we have to calibrate it. Mike mentioned that before, but that's really trying to represent actual conditions. What are we seeing for flows and pressures in the real system, so that we can match that in the model before we then use it for analysis. And we kind of gain trust in the model itself before we can actually use it for anything else. And then the last in terms of general hydraulic modeling is, once you have that calibrated model, kind of the sky's the limit in terms of what you can use for these models. I listed out some examples there of different options you have for using those models. That can be evaluating complex hydraulics, and fire flow analysis is specifically something we'll be talking about today. But you can also look at main breaks. What happens to the system if a main goes out of service? Does it affect customers, and how does it affect those customers? Looking at things like flushing programs and surge or water hammer analysis. You can also test out alternatives. So both on the infrastructure side, what if we have to take a main out of service to do a replacement, but also operationally, what if we change the operations of this pump station and drain and fill the tanks differently? Looking at future service areas, if a new development gets tied in, we can plug that into the model and see what impact that has to pressures throughout the system. As well as just general capital improvement planning, where those replacements happening, or where the restrictions or capacity issues in the system. They can also be used for advanced applications, for emergency planning, asset management, so feeding into pipe rehab and replacement programs, as well as looking at energy optimization of the pumps in the system, or real-time modeling. So kind of going one step further, and instead of saying generally these pressures are 50 psi, but right now, what is the pressure? And then the last category is just water quality. So there's a whole wealth, in addition to just hydraulics, pressures and flows, we can look at water quality conditions. What is the age of the water out in the system? And where are parts of the system where maybe they're higher water age, so the water's been stagnant and sitting out there for longer, maybe at a dead end? And how can we loop the system or put in flushing, implement flushing programs to improve the water quality? In addition to water age, we can also look at actual concentration, so like free chlorine residuals, which actually have those regulatory components that we can compare against and improve in the system. So a lot of different options in there. There's even more beyond this, but it really unlocks a lot of possibilities once you have that hydraulic and calibrated model. So getting into a couple of the specifics on the town of Newcastle's water model. So first we have the system itself, just kind of a system overview of what your system looks like. And this is a screenshot from the model itself as it's represented. So there's all the lines in here, the purple and blue lines are all water mains in your system. So there's about 132 miles of distribution system pipes. The two different colors are the two different pressure zones, which are used to control pressures in the different elevation areas to make sure that pressure is high enough for customer use. You also have 3 different pump stations in addition to, or 3 pump stations total, Millwood being at the treatment plant, and then you had Bedford and Mountain Peak booster stations to boost the pressure in certain areas of the system. You also have 4 storage tanks. So Alpine having a main storage tank and then standby tank, and then storage tanks at Hudson Hills and Whippoorwill. There's also, and Mike mentioned it earlier, about 1,300 fire hydrants throughout the system. And that's what those dots are throughout the system. So you can see they're kind of distributed throughout on all these different size water mains, as well as throughout the system. A little bit more details about the distribution system itself. For the fire hydrants, you've got different areas that are made up of these different fire hydrants. So you've got northern fire hydrants being a small portion, and then the rest being made up of Millwood and Chappaqua, just in terms of location and districts. In terms of the valves, we've got primarily 2 different types of valves. In the system, we've got line valves. So those are the isolation valves actually on the distribution pipes. If a distribution system pipe has to be taken out of service to be replaced or repaired, for example, those can be closed. And then we also have a pretty close number of hydrant valves. So those would be the valves tied into hydrants that can be closed to do maintenance on the hydrant itself. You have also, in terms of pipe length in the distribution system, the majority being cast iron lined pipe, about 100 miles. And then a very small portion being cast iron that is unlined, with about 3 miles. The remaining, about 1/4 of the system is ductile iron, about 29 miles. And then at the bottom right, there is pipe length by diameter. So you've got pipe ranges from 2 to 24 inches, but the majority of the system is 8-inch in diameter, with especially most of them being 6 to 12-inch. So kind of that middle range there. So that's the system as a whole. And when we started this model development project, we gathered a number of different sources through coordination and many different people at the town collecting information and providing it to Arcadis so that we could help build this model. This is just an example of the primary data sources. Geographic Information Services, or GIS, is the primary data source for the piping network. So that was pulled in, kind of usually that's the first step of building that piping network into the model itself. So that's what was a significant data source. We also used facility drawings to build out the different facilities, the pump stations, the storage tanks, primarily, and then the kind of being able to approximate those, where the pumps are in the facilities physically. And then adding on to that, we included or gathered things like manufacturer pump curves. So the hydraulic information that was built on top of the physical information. Information on daily plant pumpage reports and monthly operating reports, as well as customer billing data, all got fed into the customer and water use information component. Customer billing was primarily to apply where is water being used, so allocated throughout the model, where water is being used, and then the additional data being able to calculate additional flow or losses in the system, so that we approximated all the flow going into the system from the treatment plant. We also had additional information about pressure reducing valves and other operational information, how the system is typically operated. Planned improvements and developments were incorporated kind of throughout the life cycle of the project, just as they got it implemented or planned, so that we had that best available approximation of what the existing system was. And then we also used the city's flow, pressure, and tank level data, or SCADA, to help calibrate the model. That was in addition to fire flow tests from 2018 that we used to supplement that information initially. So like you can tell, there's a lot of different data sources. These were all compiled and brought into the model itself to help build and develop the hydraulic model initially. Once the model was built, it was calibrated, and that calibration is really a critical step to make sure that the model represents actual conditions, actual observed field measurements. The typical criteria from town to town or city to city or system to system can vary a little bit. There's guidance provided by the American Water Works Association and groups like the Water Research Foundation to help guide utilities and engineers and modelers to what should be followed, but there's no hard limit of specific values that should be achieved. It's kind of a system to system analysis. On the top right here is the model calibration criteria that Arcadis and the town worked through and determined for this project. All of these values are based on the AWWA M32, which is the modeling manual for hydraulic modeling that provides some of these guidance. In terms of the individual data sources, we have water levels. So we're trying to match that between 3 to 6 feet of recorded water levels for those storage tank facilities. For stations and facilities that had flow information, we wanted to be within 15% of that recorded flow rate. And then the pressures, we wanted to be within 5 PSI of what we were seeing in the system. The calibration itself, September 15th in 2020 was selected as a calibration day where we did those model comparisons. That was partially due to having additional pressure or temporary hydrant pressure loggers out in the system. So we collected additional information so that we could calibrate to more locations rather than just what was available typically. And that's what those 7 temporary hydro pressure loggers are listed there. That was added into the additional SCADA information from the city that included flow at pump stations and tank level at the different storage tanks. And that data was all compiled together and used to compare against the hydraulic model throughout the full 24-hour period. So it was an extended period, 24-hour calibration. It wasn't just a snapshot. We like to do that typically about longer calibration just to make sure that everything is working for a long period of time and you don't have things like tanks draining out too quickly. We're making sure that it's kind of stabilized. We also need that for different kind of evaluations, especially with water quality. It's that extended period component. And you can see on the bottom right there, that's a graph of showing what that comparison looked like for one specific location, where we have SCADA information here at the Millwood discharge, for example, throughout the 24-hour period in blue, and then the model is in red. So you can see that they're pretty close together. And that's what we saw generally after that calibration and doing some adjustments on the model, doing some adjustments for things like pipe roughness and pipe condition, that we were able to match every location throughout the system. So that was the primary model calibration, that 24-hour period. There was additional calibration performed also with hydrant flow tests. So 11 different hydrant flow tests were performed jointly by Arcadis and by the town throughout the system on right around that same time period between August 25th and September 9th, 2020. And you can see the equipment there, but we had digital pressure loggers that we use for those hydrant flow tests. So we collect a lot of information to be able to kind of assess what this condition, what the system is doing during those flow tests, how it's changing, how it's equalizing over time. And then once we look at all that data, we compile it into a couple of key data points. That is primarily static and residual pressures. So during each of these tests, we have two hydrants that we're interfacing with. One of the hydrants is opened and actually flowing. You can see that on the left here, where it's actually flowing water out. The other one is active, but it's not open. So we're getting pressure readings from there, but nothing is actually leaving the hydrant. From the flow hydrant, we're getting flow readings. So we can understand exactly how much flow is actually exiting out of that hydrant. And then we also have from the static, or from the other hydrant, the closed hydrant, static pressure. So what is the pressure doing when there's no flow occurring? And then residual pressure. So what is occurring? What is the pressure doing when that actual hydrant is flowing? Which is that residual pressure value. So with both of these values, with the flow and the static and the residual pressure, we were able to calibrate each of those locations in the model. This is an example location where we have static pressure observed as about a 151 PSI, and the model is about 153, so about 2 PSI difference, which is within our criteria. And then more importantly, with these types of tests, we want to see a really good match when we open that hydrant up, when we're actually flowing out of the system. And so that's that residual pressure comparison where we have observed of 139 PSI and modeled of 138. So it's within 1 PSI. That is really close for this specific location. And that's what we want to see with a calibrated model. So we did that for all of the 11 locations throughout the system. 7 of those were within 5 PSI, so really good calibration. There was a couple locations that were a little bit farther apart, but still within general guidance and general criteria. That's 6 to 10 PSI pressure range. And that is typically still acceptable, and we labeled it as fair here, but it's still within calibration criteria. There was no locations that were outside of our criteria calibration goals after we got through calibration and adjustments. So, and that's an overview of the calibration itself. What we're going to do now is move on to some of the analysis that we performed. And like Mike mentioned at the beginning, basically the big driver there was to look at and understand fire flow in the system, which is why that calibrating to those hydrant flow tests was an important aspect of developing and calibrating that model. Now, one of the things that a lot of hydraulic models are used for is to support ISO fire suppression rating, which feeds into public protection classification, which feeds into things like insurance grades and insurance ratings for the community. For a lot of these ISO fire suppression investigations, there's a lot of field testing and hydrant testing that is required for those. Typically ISO comes up with critical locations and building locations that need to be tested by the utility, that they have to go out there and test those in a certain way, and that has to be done kind of on a moving, kind of a regular basis, so that those insurance grading can be upgraded or updated regularly as well. An alternative to that is actually using hydraulic models to support that public protection classification grading. So those models, when hydraulic models are used specifically for this use case, it does have to be an all pipes model. It can't be skeletonized, which is not quite as common nowadays. We used to have some models that would be skeletonized, especially bigger systems, just because it was more resource intensive. And the cities or the town's model and most models at this point are not skeletonized. So we were good there. The model also must be calibrated. So they don't give specific criteria, but they do want it to be signed off by an engineer so that they can say that it is calibrated. And then another one of their recommendations is that calibration should be ongoing. So here we're talking about the initial calibration as a part of model maintenance and updating the model. They like to see that model be validated or calibrated into the future as well. It's not just a one-time effort. It should be continually checked on a rotating basis. And then once that model is available for, at least for ISO's use, they want the static and residual pressure, especially for those building risk assessments that they do on their end. But they can also just take all of the results for the entire system and use what they need. But they need static and residual pressure and then that available fire flow. So the available fire flow is basically the main capacity, the distribution system capacity to provide fire protection at, say, a 20 PSI residual. And 20 PSI residual is kind of the regulatory limit for how low pressure can go. So that would be the absolute highest flow that can be used for fire protection at that location. And that's what they, between the static and residual pressure and then that final available fire flow or main capacity, they use that for all their grading information on their end. So in order to support the town, we did that evaluation with the hydraulic model after it was calibrated. And this is just a view of what those results look like for the town's system. So what this is showing is at each location in the model, that color coding is just what the available fire flow or what the available capacity is of the system. So you can see those purple values are above 5,000 GPM, it's kind of the higher end of the fire suppression capacity. Blue is still pretty high at 1,500 to 5,000. That middle area, when we get into the yellow and the orange, is the 500 to 1,500 range. Still typically an acceptable range, depending on what you're looking at. Fire protection can range based on everything from land use, if it's residential, commercial, industrial, to specifically, like ISO actually looks at the different building characteristics. So is it a wood building? How big is it? Does it have its own sprinkler system? That type of thing. So it can get pretty complicated and it can vary from town and community to community, what you should be at for a given location. But that 500 to 1500 is generally still, it's on the lower end, but it's still acceptable, especially for residential locations. And then the red locations are those locations that are below 500 GPM. So you can see there's a couple pockets here down in the south, and here and there. Those are especially at locations that are higher elevations, so they just have lower pressures to start with. So it's harder to push that water up into those higher areas. So this is available fire flow. This was kind of that ISO component to be able to understand the overall capacity of the water distribution system. But it was kind of a jumping off point or to an additional analysis focused on fire hydrant painting. Fire hydrant painting is a little bit different than what we're looking at for that water main capacity. Guidelines for fire hydrant painting are in NFPA 291, which is specifically about the practice of fire flow testing as well as marking of hydrants. And in that document, they have different classifications of hydrants based on that, and they call it a rated capacity of the hydrant itself. And you can see that there's AA, Class AA, Class A, Class B, and Class C. And those are based on different flow ranges. So anything above 1500 is classified an AA classification. And then from there, then they correlate that to a specific color. So an AA is light blue, all the way down to a C if it's less than 500 GPM. That would be a Class C, and that would be red in terms of how you're actually marking that. And that marking usually is on the top of the hydrant, not the whole hydrant itself, but on the top. And that's typically used for just a signal for, safety and condition of what to expect from that specific hydrant. Once say a fire department goes up and tries to fight a fire, that Class C would be an indication that it could be a specific range of flow that they could expect. Now, that rated capacity is a little bit different than the available fire flow that we were talking about before. The available fire flow is more of a metric of the water distribution system. So it's kind of at the water main. So say an 8-inch pipe, for example, going through a neighborhood, you might be able to get 3,500 GPM off of that main, but that doesn't mean that the hydrant rated capacity is 3,500. You can kind of see that in the diagram where there's basically additional piping and additional losses that happen between the water main and then the hydrant itself. There's a hydrant lateral, usually a 6 or an 8-inch pipe connecting the water main to the hydrant itself. There's also isolation valves, additional minor losses, and then you have losses throughout the hydrant itself as it kind of pushes through the hydrants, and usually those are a smaller diameter to the actual port itself. So after the model was used to find the available fire flow, additional information was collected on each of the hydrants to understand things like their the manufacturer and the specific losses that would the pressure losses that would occur through that hydrant barrel based on that manufacturer and based on the specific hydrant types. And then those were added on to the original model results to kind of figure out what is the actual hydrant rated capacity that we could expect out of that hydrant itself. It's a combination of measured values, like I said, the information about the hydrant itself, distances of this pipe length, for example, and then there were some assumed values just because there was some unknown values or uncertain values just associated with the exact characteristics of some of this piping. But those were all used to calculate that rated capacity. It was kind of an iteration to find out how much more losses there were. And then ultimately we came up with that hydrant rated capacity for each hydrant in the system as well. And that was used to equate those to different NFPA classifications. So these are the same classifications that we talked about before, with AA, A, B, and C ratings, and their corresponding color that they would be marked up if you were to use that for hydrant marking efforts. You can see most of the system, 924 hydrants would be that AA blue classification. There's a handful in that middle classification, from 500 to 1500 in yellow and orange. And there's about 25 hydrants that are in that C red classification. And they're kind of, the results themselves are pretty similar to the available fire flow. You can see that there's some pockets of red here and there. General areas are similar, but the individual hydrants are a little bit different here and there, just with those additional calculations. And so that was I think the last, at least, fire protection analysis that we wanted to talk to, and I'll hand it over to Mike if you want to talk about next steps.
Thanks, Ben, for that. Could you just back up one slide?
Yeah, yep.
Just to reiterate a point that Ben just made, you know, the blue and the yellow are in the recommended range. So almost 90% of the fire hydrants within the town are in a recommended range with fire flows above 1,000 gallons per minute. The red section, which, as he shows with the dots, they're rather scattered, and that represents something like just, I think, under 2%, 25 hydrants right now. That would be at that less than 500 gallon per minute range. So probably just good information to be aware of. There may be some dead ends that maybe over time could be addressed. So as far as next steps, you can just fast forward there. Yeah, one slide. So what the town, or basically the insurance services office, ISO coordination, we did circle back with those folks. Bart and I have been in communication, and they have accepted the model. They accept that the fire flows can be determined from this model that was created, that we followed all the AWWA standards and gave them the data set. There is this information. I know we have a lot of fire officials here tonight to understand what the values are and a possible marking system, so they could be marked in the field as such. And then, as far as moving forward, we have put together a proposal for the town to do some ongoing maintenance of the model, to look at maybe a deeper dive on some of the problem areas, to do some of those runs I mentioned earlier for capital planning. Maybe a developer is coming in to do some future commercial development, and this is the type of model that could be utilized to right-size piping or maybe to address some ancillary areas. The model could be further expanded. I know we threw a couple of ideas out to the town about some additional analyses that could be done related to the system operations or water quality or different type of scenarios. The town may want to do a couple of hydrants, or I'm sure they do some hydrant testing on a regular basis. So that's the kind of information that could be utilized back into the model to make sure that everything is staying up to date and it's a calibrated model to be used in the future. So that's kind of our overview of what's been done and some ideas and suggestions for what you could do next. We'd be happy to answer any questions that are out there, or walk you through some of the background if necessary.
And if I could just add on just quickly a little bit before we get into the questions, and just go through what we did from the town after we got all of this information. I think it was around early March that we got the list of the rated capacities, the NFPA 291 rated capacities from the model, which told us how the hydrants should be painted. So at that point, we went out and we looked at every hydrant and wrote down the color that it was currently painted at that point to identify where there were differences. So this was from back in March. In Chappaqua Fire District, we identified 109 fire hydrants that needed to be painted to a lower color. And we identified 175 hydrants that needed to be painted to a higher color. In Millwood, we identified 33 fire hydrants to be downgraded in color and 125 to be upgraded. Nobody's here from Northern, but they had 44 that were downgraded and 62 upgraded. It was 548 hydrants. We have since that time repainted all of these hydrants. So our understanding is at this point, every hydrant in the district is painted to the expected flow that the fire departments should be able to get from that hydrant.
I could ask a question. Like when you showed the test cases and you showed pressure of the hydrant that was being operated, and then the static pressure, and then the residual pressure one hydrant back, if I'm correct. With that, was there also a confirmation analysis of the actual fire flow of the flowing hydrant?
Yes. So the hydrant that was flowing, and it's kind of hard to see in there, but there's a pressure meter that's collecting pitot pressures that is converted into a flow rate. So that's kind of a collected information point.
Okay. And those flow rates, I saw it seems like your analysis is pressure driven, and you want it to be within 5 psi when you confirmed the modeling, and so your analysis of GPM is all driven off that pit dot valve, all driven off those PSI measurements. Is that correct?
Right.
Okay.
At least for these, especially for these hydrant tests, because with this calibration, like we're collecting this flow information, but then we're plugging that flow into the model and then testing against the pressures. We did have flow information, I think, at the pump stations to calibrate against, but that's the only flow that was calibrated. No, the rest of it was pressure based.
Okay.
But I want to just make sure I understand your question, because when we're doing the flow and getting a flow rate out of that hydrant that's shown in the picture here, we're doing the analysis to take that down. But is it to 15 psi? Is that what's recommended as far as bringing the pressure down to get available fire flow?
Well, 20, I think 20 is the recommended. Yeah.
Okay.
Right. Yeah. The 20 is the for the available fire flow, like the total capacity. During the test itself, we do want to see a observed pressure drop of a certain rating. Depending on if you look at NFPA versus AWWA, that value is a little bit different. It's like 20% or 10 psi. And so that would be the 151 to 139. So we're kind of seeing a pressure drop in the residual hydrant based on whatever's flowing. And I don't have what that flow rate is. But that's just kind of a test criteria, so to speak.
Right. That was my question. It was just driven to see if there were actually substantiated GPM flows in some of these tests and some of this modeling. That was.
Mm-hmm. Yep.
Yes, but you would need take it down to 20 psi to get the maximum available fire flow. Presumably you would need a pumper truck, right?
Yeah, you would have to, if it's exactly, if it's 150 psi hydrant static, then you would have to put into a centrifugal pump. I mean, that's one way. That was exactly my question, whether,
Yeah, I thought that's what you were asking. That's why.
Yeah, with that testing you were doing, was there any way to specifically substantiate the fire flow in a certain section or on a hydrant? But you answered the question. I mean, it's all pressure driven, but I was just curious.
Yeah, and for other systems, sometimes we do use, like you can see from the picture, you're doing the 4-inch at the front. Sometimes we'll open up even multiple ports just to try to get more flow out. But yeah, in this condition, we wouldn't have gotten that much more out.
Or Chris, Riverwood's included in this? Is that private or town-owned hydrants?
Riverwood is down,
Okay.
yes.
I couldn't
Yeah,
remember.
that's fall within the Northern organization.
I couldn't remember if that was private up there.
No.
Chris, this really isn't specific to the presentation, but just we just had our engines had the pump tests performed on it, and a couple of the trucks they did find some gravel and rocks that had either bounced up against one of the screens that protects the pump, or a couple had gotten through. When you guys do water main repairs, and I'm assuming this is probably one of the main ways that rocks and all get into the system, could we possibly work on a plan where the next hydrant downstream, once the main is connected, flush it for a good 15-20 minutes to try to get some of that gravel and rock out of the system to try to save some wear and tear on the engines?
Yeah, absolutely. I mean, that's our normal, operating procedure always.
Okay.
After a water main repair or installation is definitely thorough flushing. Both to clear out any obstructions that might have entered the pipeline, which we're always careful about. What we the pipes clear when we put it back together, and also we want to turn the water over just for water quality reasons. But yeah, typically we always, after our repair, we'll flush for sometimes up to an hour or so, while we're cleaning up and backfilling and stuff.
Great. Okay. Yeah. No, and I'll have. I mean, we're trying to instill in our guys too a proper flushing of the hydrant before they're connecting hoses to it and all like that. But the heat of the moment, sometimes people forget on our side. So it was just fresh in my mind because we just had the pump test done last week, so that's why I brought it up.
Right. And one other thing just on that is sometimes we're finding when new mains are constructed, if it's like real gravel, that's probably more the likely source for that. So anytime we're taking on new mains, we're flushing those systems out. And also with our annual maintenance on the fire hydrants, when we're going around winterizing now, we're actually flushing those at a higher velocity than we used to in the past. And that will clear out. I don't know exactly what it looked like, but if it wasn't gravel, it could be like some tuberculation that was inside the hydrant. So we're trying to flush all of that out as well when we're doing the annual maintenance.
Great, thanks.
Will me and Bobby do those tests? A bunch of those that we float are disgusting amount of crap that comes out of that.
Yeah, I'll bet you I'll go across.
Yeah.
That was from the construction crew.
So much more scale. Yeah, those are existing stuff here.
Anybody else have
Yeah,
any
just to
other-
confirm, so
We got
according to NFPA, the colors, just so we're all on the same page, so 1,500 gallons per minute or better, we're gonna go with a blue,
Yes.
right? So that would be the caps, the 4.5 steamer, and the dome, whatever else, bonnet. And so the next level down, what are you using? Are you using green?
That would be green.
Okay.
I think it might have been.
Right, it shows as
Yeah, I think it's
yellow,
accidentally
on
yellow.
a couple of the models,
Yeah.
it shows as yellow,
Yeah.
because the barrel, the main part. So we're gonna use blue, yellow, orange, red. You're gonna use,
Yes.
that's what we're aiming for, right?
Blue, green, orange, red.
Correct. Yeah.
Right, yeah.
Okay, good.
Unless you live on Stornoway, there's a lovely shade of brown we're shooting for.
Yeah.
Didn't do that again, did they?
No, last time I drove by just to check, it looked like it was still regular, but I do chuckle every time I go down Whippoorwill.
Yeah, it's been about 2 or 3 times I think we've repainted that, and oddly enough, the color that sometimes changes to is the same color as the siding on the house nearby.
And the last name of the owner of that house.
Yeah, we have spoken with them, and hopefully it doesn't happen again. But we'll definitely keep an eye on it.
Yeah, we'll send the fire marshal after him.
And just for everybody's information here who's not familiar with it, sometimes people don't like the fire hydrants in their front yard and they have painted them brown or something to try to have them blend into their landscape.
Or planted rhododendrons and boxwoods around them, fences.
Yeah.
The only thing, my last comment to the gentlemen who are helping with this is that, I can't unilaterally commit Millwood, but if at some point in the future to substantiate, actual field flows, I think, Millwood would probably be, willing, one time we'll pick a hydrant, won't be in the way, and we, in terms of, confirming the accuracy of the modeling, we can actually measure the flow. We have GPM flow meters on some of our apparatus, not all the apparatus. I know in the past, Bart, remember we went up when the Hudson Hills
Oaks Cross Road.
tank was, and we helped you kind of establish and define some, parameters
Bring
there.
up a thing with Sunshine under construction, finding the closest town hydrant out there wouldn't be a bad idea. See what the flow is we get from the closest town.
Pretty
town
far
hydrant.
away, Austin.
No, we're
I know,
we're gonna take that.
Yeah.
Doesn't that
But-
have to be done to check the actual flow at the hydrant for a certain percentage of the hydrants? Or else, this is all becomes theoretical if you're not getting what you're expecting at the hydrant.
That's what you guys have.
I'm sorry, what was the question?
So this is, yeah, and I'll make a comment and then maybe, I don't know, Ben, if you could add in. But as part of the calibration process for the model, multiple flow tests were done and they were compared to the model to get them within that criteria. We would also, before the model was done, we were doing flow tests ourselves in-house each year. All of those records, I don't know, we at one point did like 50 in one year, were all provided to each fire district. If there are any specific hydrants that we don't have test data on, that we've done an actual test, not we have the modeling on everything, we would be open to testing those locations. Part of the reason for doing the model is in that in some areas, doing a flow test is just not possible. It's based on the topography. You have people downhill from the hydrants. When you do a flow test, you're moving a lot of water and you could really make a mess in somebody's property in a couple of minutes time. So, but we are open to
Water main, too.
doing other actual in the field flow tests at locations if you have areas that you'd like to see those done. We're more than willing to work with you. That's why we did all of this and to try to get the hydrants painted as accurately as possible.
And not to just jump in, but I think a good example would be Paul, if you remember, I think it was brought up to us a question about Bessel Lane.
Right. Yeah.
We just did recently test that area, and confirmed that, what we had believed that the color scheme was accurate. So I'll share the actual results with you shortly. We had just done the test several days ago, so I'll
and I
share
think,
that
Chris,
data.
to your point, that's the perfect example, I think, of how we're working together with this. Because, I mean, I had called you the day after the fire and just said, hey, we kind of thought it was a little low coming out. And, you looked up the data, said you definitely would get out there and take a look at it. And, said it would probably be closer to the fall. But I think kind of where we've gotten in the relationship, at least with Chappaqua and the water department, I think we're in a better spot than we were previously, as far as with just an openness and working together without pointing fingers and yelling and screaming. So.
Yeah, I agree, Ed. We definitely want to continue to work with you guys, and anytime anybody has a question or wants something, validated, more than happy to, work together to get that solved.
Absolutely. We understand and appreciate the volunteer service that's provided to the community, and we want you to go there and get out of the hydrant what is indicated. We know that it's an important safety matter for you guys.
Yeah, and I don't, like Bart said, I don't think our goal is to get away from doing flow tests, at all. But like Bart said, there's certain areas where it could create a major problem. So we would like to rely on this model to maybe reduce the amount of actual field tests that are being performed. Or to aid us in areas where, you know, it's just not practical, you know, due to traffic or topography, stuff like that.
So Bart, the 1341 just probably doesn't include the crossing, right? Since those aren't dedicated yet, pretty much. That's another 22 or 24, something like that.
Correct, yeah, that'll be changing.
Yeah, once we take
you know,
ownership
there's
of
the
it.
retail side that I think will.
Yeah, that's just 20, and then whatever's
and then
inside
the
is the
village,
townhouses.
probably another
Right, and then the
close to-
East Village also.
Yeah, so probably another 20, some other 40, give or take. Okay.
Yep.
It's a decent number.
So Commissioner Shapiro, you know, to answer your question, in NFPA 291, the GPM is theoretical and it is pressure driven. So, you know, one of 4.3.6 to obtain satisfactory test results of theoretical calculation of expected flows or rated capacities, sufficient discharge should be achieved to cause a drop in pressure at the residual hydrant of at least 25% or to flow the total demand necessary for firefighting purposes. So even under the NFPA guidelines, it's driven by water main size, by pressures as obtained from the pit-out valve, and then one or more hydrants for static, and then residual pressure once one or more hydrants are flowing. I just asked because, you know, it would be nice to do it, actually do it one time, and you know, maybe we could work that into this model.
Right. Okay.
Right, and we're open to that, but as you know, Greg pointed out, that NFPA 291 does accept the theoretical calculations.
Which you guys have been fantastic about doing already.
And Bart, we've actually approached them and they're fine with this. They've accepted it, correct?
Not NFPA, the ISO has accepted.
ISO, sorry.
Yes.
So Ben, if the request was to try to get more actual flow out of an hydrant, you said that we could open up the side portals. That would be without any other things we could do there besides hooking up a pumper truck and.
Yeah, you could do.
Pulling it
So
out?
we've done tests with multiple ports open, multiple hydrants. You can open up multiple hydrants, or yeah, do some kind of pumper truck. It kind of depends on, like we were talking about, the feasibility. Can you find a place that you're not gonna flood out the road just because that's can be a lot of water.
Right. Yeah, and then obviously you have thrust blocks at these hydrants, right? So you have just other issues that may arise to
Right.
do like an actual test to try to take that much water out of a point or an area. So it's definitely something to consider.
Right, and that's from the distribution side. That is a concern as well. So we have had water main breaks at the same time or after we've had firefighting incidents. So it is a
Exactly.
concern for us. So when you're moving that much water, guys, so the mains, typically you don't want to have the flow over 10 feet per second velocity, right? Thereabouts. I mean, when you're doing a fire flow test, you're going over that. So you're really stressing the system. You can cause problems, especially if it's not slowed down very, very slow. You cause a water handling. So that's why we look at the locations where we're doing these things and plan it out very carefully.
Yeah, and my comments weren't so much looking at a shortcoming. It was a question like
Right.
just wondered, was there an actual flow analysis other than the calculated theoretical?
Right,
But
yeah,
that's
right,
right.
yeah.
It's,
Well, that's because there was the, did you mention, was it 11 actual flow tests we performed? I think it was in the year 2020, I recall, because I know I had done some of them myself with some of your staff members. I remember Nitty was on site with us as long as an assistant. So we definitely did the 11 with you guys for that. And then like Bart had
And
mentioned.
they've all Right, yeah, they've been out of a single 2.5-inch port, so.
Right.
Yeah,
Right,
what
right.
we've done,
Those
yeah.
were, those were the pressure driven, those analysis were the data was driven by pressure. I just was asking whether there was any.
Well, he said there was some that was done through the flows from the pump stations, right?
That was part of the data.
Part of this data that was
yeah,
curious.
Was that data calculated during the flowing, specifically during the flowing of those hydrants?
That would be a question for Arcadis.
No, that was during like just a typical day or like a max day, I think. So not during the flow events, but just throughout the normal day.
But that may be a way of achieving the same, same data.
And so that also brings up, I think, a good point, Ben. I don't know if you want to touch on it more, but I think a lot of these numbers were based on a maximum day. So when you look at the water system, usually the max day is kind of in the summer. And that's the demands that are all going to everybody's houses and whatnot. So, and in doing this, we were conservative. So if, we thought it was like, 975, it was like 950 or 900. The numbers were done in a conservative fashion. I think you would agree, Ben, with that?
Yep. Yeah, and that's typically the case for water evaluations. Looking at a max day, it's kind of conservative. It's not the worst case condition, but it is pretty conservative because on an average day, you probably have more capacity.
But again, we are open to.
Like I said, it was more of a question than a
Right, yeah. And we do when we do our in-house flow test, what time do you come in, Chris?
Early.
3 in the morning.
Yeah, so we do it when people are not using the water.
Chris, like you said, like we've increased and down and obviously decreased in some areas. So there are places where we saw like a large quantity of increase and then others like a large area where it decreased in certain spots in town, or is it?
You mean like the residual?
Yeah, the flows and everything. You're saying
Color
we saw a lot of the color coding, we increased a lot, but then there was some decreases. Was that?
Correct, yeah.
Was there some areas where it was?
I'd have to kind of lay it out on a map and see if there was like certain areas, like I know like with Millwood, like there was like a lot of hydrants that would be like along like transmission mains that like, we upgraded a lot of that stuff.
So we increased the flows.
But yeah, if you want, I could look at kind of like localized.
And I was just curious, like any area where they said we had some of the colors go down, it's like, oh, is this something we have to look at? Or
Yeah, I'd have to kind of look through it to kind of give you,
Yeah.
a better answer on that, but yeah, I can definitely look at that,
Is there a way to get like a digital copy of that map? Because I know at least in Chapel Chiefs cars, we have the hydrants in our tablets with the GPS coordinates, and our software has the programs that we can put the water main and the flows and data into that system through the company that we use. Is that a possibility?
We could give you the hydrant numbers and the flow number for each hydrant.
That would
on
be
a
great.
Spreadsheet.
That would be great for
Yeah.
Millwood, yeah.
Usually the map books and that'd be good.
That would be great.
And they were all, that was another thing we did. We put tags on each hydrant, and that was to facilitate any problems that you see out in the field, reporting to us, so we know exactly where it is and we can go and take care of any repairs or maintenance in a timely manner.
Chris has been great. He's very communicative. Every time this hydrant out of service goes back in service, he lets us know. We do it by numbers, by addresses. It's been very good.
So we'll send you the spreadsheet, of the hydrant numbers and the flow.
That'd be great.
Also, I know Kellen does a lot of the maps and everything with the collector app. We update that, we can input it into his, like the Chapel Cheese cards with the PDFs and everything with the collector app. Because Kellen's got all those maps and everything, but I know we did that before with some of the hydrants. So.
Yeah, that's something we could explore. We
Yeah.
have to look at that. What would be the best way with the different software and how that works.
Paul, I don't want to speak for Paul. We have to check with Alpine Software and see if they can.
Yeah, no, definitely.
Ben or Mike, I just had a quick question, like in regards to when it was mentioned about like a ongoing calibration. I guess would it like a good example of like that be if we, took on a capital improvement project, and, replaced and upgraded the size of a water main for, a street in town. And upon completion of that, did a flow test or several flow tests. We would work with you guys on, submitting that data to you guys to, integrate it into the model. As I'm assuming how something like that would basically work.
Yes, exactly that way. Relatively straightforward. I think we gave an on-call like a service agreement, so it would just be like the few hours it would take to put that into the model and report back. I'm assuming the town, I think, talking to Bart and Chris, I could think that there's some relining projects that go on from time to time. I think there was several miles still of unlined pipe in your system. So yeah, those are things that you might want to plan for in the future, and it would be good to reflect that back in the model when it's done.
Okay, so upon
so
the
our
completion
outage-
of, right, so upon the completion of any type of project like that, we would probably consider doing an actual flow test and relaying that information to you guys.
Yes.
Right.
And then I think there was Mill Road or Mill River Road, Bart, that there's the RFP out for.
Yes, that's for the.
Whether it's going to be a 12 or 16, like that's where the model could be really helpful in looking at the impact, right? Because the one thing the model shows, right, size doesn't always matter as far as getting the flow out. There's so many other factors that matter here, and so being able to put in a 12-inch is obviously saving the capital dollars. So it's another great benefit. It's just maximizing the dollars that you are spending.
Good.
Well, thank you very much. Thank you. I appreciate it.
For sure. Hopefully we met your expectation. And we'll certainly circle back with Bart and any follow-up items, and look forward to working with you guys in the future.
Any last questions, takers? Anybody online? We put a lot of effort into this. It's been a long time coming. It took longer than we expected. I think COVID slowed things down, but we're happy with where we're at and having the hydrants repainted this past summer. But really, any questions while we have Arcadis on? Any other questions at all? Please just ask.
Bart, I definitely do have to echo Greg's comment about working with Chris is just fantastic. It's an absolute pleasure. He really does a great job keeping us informed. John, not so much, but we've learned to live with him.
Hey,
Bart.
Yes.
I got a question. Is this model are we going to continue doing testing, or is there how is it going to go on continually? Next year, are you just going to test 10 and then go back to the model and then going to revisit it again? So how's that going to work?
Right. So any changes, water main construction, they would be added into the model, but we will still continue to do a small percentage of flow tests each year, but we don't have the intention of flow testing all of the hydrants because we know there's some that just really are not practical to test. And again, if you guys have lists of anything that you'd like us to do, we'll take a look at it for sure. But we will still continue to do some flow tests in-house each year.
Jill, what is our current hydrant contract call for as far as flow testing goes? I don't remember off the top of my head. Do you?
I can do it.
Oh, go ahead.
Oh, well, go ahead, Jill. No, I'm sorry. I didn't mean to.
No. I was going to be present, but I'm just not feeling that great, and I decided I would not get everybody upset.
Yeah. So the current contract calls for flow test the hydrants every 7 years according to the NFPA 291, unless ISO provides written notice to the water district and the fire district that it will accept the water district's proposed hydraulic model and representative sampling.
Right.
That's our
So,
current contract.
So we have been doing that up until this point with the intention of having ISO take and accept this hydraulic
Yep.
model.
And that's fine.
Speaking of the contract, so this is the last year of the current contract. We actually weren't going to disturb the contract. What we were going to do is issue an addendum that would include a 1% increase for the next 5 years, so each of the next 5 years. And we have communicated that to each of your treasurers, because I know that you guys are, creating your budgets for going forward.
Yep.
That will be coming out shortly, but we wanted to have this meeting first.
Sounds good.
So I
All right.
didn't have a question, but I wanted to thank you guys at Arcadis because it has been a very useful tool to us, right off the bat, especially with, determining, hydrant coloring schemes. So it's been a time saver, for us already, and I'm sure the more familiar we get with it, the more uses we'll find for it. So I just wanted to say thank you for your efforts there, and I wanted to say thank you to you guys with the fire departments, because you guys have been great working with me, and you guys I came into this not too long ago, and I appreciate you guys reaching out to me with your concerns and letting us look into it and get back to you. So I appreciate the way we've been working together recently. So thank you for that.
Yeah, I have to tell you that on behalf of the town, number one, I'm truly impressed. Bart, Chris, John, you did a fabulous job. Thank you so much, Arcadis, for pulling this off. But I just want to tell you how much we truly value our relationship with the fire departments. Whether it's been just a changeover of staff or personalities or captains or chiefs or whatever it is, we're really thrilled with the new chapter that we've entered into, and we'd really like it to continue. So thank you so much for being open and for working with us. It's made all the difference, and looking forward to a very successful future as well.
Great.
Yeah, I was going to just thank everyone for their time this evening. I know I heard Nidhi's name she was out there for the hydrant testing. She is still with Arcadis, by the way, but she moved to California to go back to school. So I'll let her know we heard her name drop tonight. So I'm sure.
Yeah. Tell her we said hello, and we're glad she's doing well. She was a pleasure to work with in the field, and just through email and phone conversations. She was great.
Great. I'm sure she'll love to hear that. So thank you all for your time, and I guess I'll sign off here. Have a great night.
Okay. Thank you. Thank you so much.
Thank you. Thanks,
All right,
everybody.
Good night. Bye, guys. Thank you.
Bye.
That's it. Everybody's good?
So,
Good night. Have a good night.
all right, bye.